This question is meant to cover all the bases of anything you encounter with acid-base problems. I'm going to introduce you to a framework that should help. There are three things that you need to check whenever you're looking at acid-base. The first is the pH. That'll give you your primary condition. The next is whether or not your bicarb, or your carbon dioxide is compensated correctly. And I'll give you your secondary condition. The third is your anion gap. An important thing to note is that your anion gap will only give you information concerning metabolic acidosis. It will not give you any other information. But you still need to check it, and this problem exemplifies why. First, let's look at the pH. We have 7.6, which means we're in some kind of alkalosis. If we look at our handy-dandy equation, H2O plus CO2 turns into bicarb and hydrogens. Okay. Our bicarb and our CO2 are our levers. It's what our body regulates. The bicarb is regulated by the kidneys. The CO2 is regulated by the lungs. We can increase bicarb reabsorption in the kidneys, putting it in the blood, or we can increase respiration in the lungs, decreasing our CO2 load. Looking at what we have, you'll want to remember these numbers. A normal bicarb is about 24. A normal CO2 is about 40. If we have more bicarb than normal, it's going to drive the reaction this way, and we'll end up with less hydrogens. If we have more carbon dioxide than normal, it'll drive the reaction this way, and we'll end up with more hydrogens. Meaning that if we have more bicarb, we'll go alkalotic. And if we have more carbon dioxide, we'll end up with acidosis. We're dealing with aklalosis. We have more than normal bicarb, more than normal CO2, like this, what's in red and green here. And so we're dealing with kidney issue, alkalosis, because that's the one that fits. The respiratory acidosis is trying to compensate for alkalosis, and we know because of the pH. So, in this case, let me get rid of these boxes and underscores. We have metabolic alkalosis. Number two, we need to check compensation. I'm going to pull something out of our lab that is given whenever we have problems like these, and it's the compensation values. We are looking at metabolic alkalosis. We should expect an increase of 0.6 CO2 per 1 increase of bicarb. Our increase in bicarb is 11. We have 35, 24 is normal, so we should expect an increase of 6.6 CO2. What we actually see is an increase of 30, which means that our ventilation is way down, or there's another issue with CO2. So somehow, our respiratory system is way overcompensating. So we're going to say that in addition to metabolic alkalosis, we have a respiratory issue. And according to our little chart, if we have too much, and that's going to drive it this way and increase our hydrogens, so we're going to have respiratory acidosis. It's weird that we can have both, but we do. Our metabolic alkalosis is our primary condition. Respiratory acidosis is our secondary condition. Now we need to check the anion gap. Even though we're not dealing with metabolic acidosis yet, we need to check because we might be dealing with it. So let me get rid of this, these compensation values really quick. Just erasing things we don't need right now. Getting rid of that. Okay. Anion gap. I'm going to grab a different color. We have 146 millimoles per liter of sodium. I'm going to say it's this much. Our body has to maintain electrical neutrality. Sodium makes up nearly all of our positive charges in our blood. Our negative charges are separated into a few things. We have our bicarb along with our chlorine, and our chlorine is 89, which leaves us with an anion gap of about 22. A normal one is 12, and the cutoff for a large anion gap is about 20. So the rule with anion gaps is that anything over 20 is large anion gap. Okay. If you don't understand this math here, it all needs to equal 0. We have 146 positives, 35 from our bicarb plus 89 negatives from our chlorine has to account for everything but the anion gap. And then we just set it all equal to 0. Okay? And so as a tertiary condition is a large... I'm just going to do this. If you remember what I said earlier, it only gives us information about metabolic acidosis. And so our answer is 2, 3, and this is wrong. I'm going to say 5 and name this acidosis. If you were confused, you were right to be confused. We have metabolic alkalosis, respiratory acidosis, and large anion gap metabolic acidosis. You can have all three.